interesting thing, when we have one category, click-through rate is 3% more than we have different categories. Still, we want to diversify it because not everything is about click-through rate, but our revenue increases. Sometimes you can have same revenue but satisfy more people, right? You're keeping revenue the same, but you are increasing welfare, but your click-through rate decreases.
Mechanism that combines quality and cross-item interaction scores. We propose two machine-learned scalable sequential ranking policies and compare them with the ad hoc push-pull mechanism in production in terms of the three fundamental mechanisms identified above. We first explain, in brief, the underlying statistical models and model inference schemes to train these policies, and then elaborate on the implementation details for the query serving time policy in the next section. Statistical framework for set ranking. In order to understand the difference between set ranking models with the standard item ranking models, we describe the underlying probabilistic models for the page conversions and view training as a likelihood maximization problem, given a proper parametrization of the probabilistic model. For a given query and a set of candidate items and a ranking pipe, based on a ranking policy theta, parameterized by theta, we develop statistical models to explain conversion on a search result page, equals 1 pi, theta, and learn theta by the following.
Probability of sale
Maximum
given.
likelihood inference problem, theta, equals.
So what is it? We have a query queue, then for that query we have DQ, which is list of items that are candidate that can be shown. Then we have a ranking pipe, which is based on a scoring function f theta, ranking policy f theta prime, f theta parameterized by theta. We develop statistical models to explain conversion on a search results page. Okay, so probability of sale, given that we are ranking based on the ranking pi and f and theta, and based on the retrieved items being DQ. And learn f theta, okay, by following maximum likelihood inference problem. Maximum probability of sale ranking increases the probability of sale. Detailed discussion on enriching the underlying probabilistic models that define ranking policy inference problem. Okay. RLTR, is it learning to rank?
MLRLTR. Standard set oblivious DCG model treats conversion probability on the page as a union of independent slot level conversion events.
Conversion.
Dependence of conversion events at different slots to the placed items. We can learn individual item quality scores by optimizing DCG with the standard lambda mart technique. The theta 0 context-aware DCG has similar loss function, but instead relies on an item context-dependent predictor. 3. We wanted to analyze the conversion rates in the multi-UVCC test, where for a select set of queries, the same query has a single category in control while it has multiple categories in the test. It appears, though, that
okay. The context-aware DCG has similar loss function, but instead relies on an item context-dependent predictor. So G of D, what is D? D is f theta 0 of D and Q. Q is the query. D is, so G of DQ and D of Q and D, G theta 2 of F. That depends on the feature both on the quality score F, trained on a standard DCG and cross items interaction, similarity of D and the, oh, D is the generated item. Collecting trading data for the item context-aware DCG model is similar, except that within a query context, we sample the positive examples items with engagement events. Like before, but for negative examples, we sample all the skipped items that were ranked above their engaged item in the log display. The representation of each record is okay. I didn't get it, to be honest.
Collecting training data for the item, context-aware DCG model is similar, except that, within a query context, we sample the positive examples, items with engagement event, like before, and but for negative examples, we sample all the skipped items that were ranked above the engaged item in the logged SRP. The representation of each record is now dependent on the individual item's representation and the representation of
This
the
is a
items
very
ranked above it,
good
up to
text,
properly defined.
because now we know how
Data
they
2 is
model,
linear.
how they
We can
think
use
about
data
it.
2. Attention window. If we consider to be a GBDT, we can use lambda mart, and if DCG weighted cross entropy and train a logistic regression function. The details are elaborated in the appendix. DPP. In the determinantal point process model, we explicitly define a probability distribution on sets based on the determinant of a suitably defined kernel matrix, proportionality, which in turn defines a trade-off between the quality and diversity to discriminate between desirable and undesirable sets. For discussions on modeling and parametrization of this model, please refer to the appendix. For training the model, we need to collect desirable and undesirable sets as training data and train the DPP on a binary cross-entropy loss. To make the problem computationally tractable, we bound the size of our records, sets of items, to be a constant less than or equal to 5. A desirable set is a subset of subsequent items in a logged SRP such that it includes an engaged item. We explore different constraints on the position of the engaged item in the collection. For negative case subsets, we will take subsets of subsequent items in a logged SRP such that there is no engaged item within or ranked above the subset. Implementation. In order to consolidate the new design, we elaborate in this section on the essential mechanisms identified above, and their corresponding technical components, for the proposed algorithms, MLRLTR, and DPP, and compare them with a simple baseline mechanism based on naively matching the impression distribution and the demand distribution. 1. Producing pointwise quality score for items. Base. We rely on standard ranking scores produced by the second round ranker as the quality scores. MLRLTR, DPP, we will still rely on standard ranking scores, suitably normalized. 2a. Defining cross-item similarity in the search context. Base. Item similarities in a given query context are computed based on a simple, one-hot, representation of the items based on a set of global aspects. Each coordinate of the representation vector is an indicator variable. 1 equals comma, where A is an aspect name and B is an aspect value, and 1e is the indicator function for the event E. For example, a new 1, 0, 0, 0, fixed price, 1, 0, item, we have a vector representation as follows. Equals 1, equals set membership symbol.
Okay,
set membership
that's what
symbol.
we need to learn. That's what we need to learn. Okay, that's what we need to learn. 1. Presentation. So that's one thing we need to learn for sure. We need to learn the language. This community talks, they have their own variables, they have their own way, they use vectors, they have this like aspect stuff. We need to learn this. All right, it's not very difficult, makes sense. A's aspect name, A stands for aspect. So what is D? I lost D. Where D showed up first time? Capital D is the list of candidate items. Alright, there is no D before. Okay. D is an item. So each item was shown with a vector D, VD. D is item. Okay, I guess D is item. And DQ is the list of all retrieved items for query queue. So these items. DQ, these retrieved for the queue. And what is pi? Pi is the ranking. Which is arc sort of F. Which F is ranking policy, F theta. F theta is called ranking policy or scoring function. Parameterized by theta. And we want to do probability of sale equal 1 given the ranking and the retrieved items. And we want to learn F. That maximizes this probability. Yes, that maximizes the maximum likelihood. Now let's go MLR-LTR. Standard set oblivious DCG model treats conversion probability on this page as a union of independent slot level conversion events, oblivious to the dependence of conversion events at different slots to the placed items. Well, of course, right? It's oblivious, like number 1 and 2 are similar, one of them will be chosen. They affect each other. We can learn individual item quality scores, F theta of D and Q, small d, right? It's called individual item quality scores. Optimizing DCG with the standard lambda mart technique. What is a lambda mart technique? Okay, it's a technique. I don't want to get in details of it. Lambda mart technique. The context aware DCG. So this one was set oblivious. The context aware DCG, it says, okay, now you are putting two items D and D prime that are similar to each other. They affect each other's probability of sale. All right. Has similar loss function, but instead relies on an item context dependent predictor. Item context dependent predictor. So G of D Q, small d, Q, and D of Q smaller than D. Okay, what is D? D is the lowercase d is the item, Q is the query, and D of Q less than D is all the items retrieved that are above D probably, right? And it equals to G theta 2. What is theta 2? Of F theta 0 of D and Q. F was the ranking policy, right? And then similarity between the product D and other retrieved items for query Q. So this context aware ranking DCG says it depends on the ranking policy and where the product D stands for query Q, plus the similarity D has with other people. That depends as features both on the quality score F theta 0 DQ trained on a standard DCG and cross item interaction similarity, which is depends on theta 1. All right, that is called cross item interaction. Collecting training data for the item context aware DCG model is similar. Oh, collecting training data for the item. I feel context aware needs more links, right? They're linked. This item with that item. Are they similar? How is it? So you need probably more complicated data set, but they are saying collecting data for the item context aware DCG model is similar, except that within a query context, we sample the positive examples. All right, what are the positive examples? We sample the positive examples, items with engagement event like before, and but for negative examples, we sample all the skipped items. So, well, here is the blind spot, right? Everything that a customer engages well, even that is not true, but they're assuming that's a positive interaction. However, it can be something a customer looked at it and said, oh, actually that sucks, I don't want to buy. So they're taking all of them as positive. And everything that the user didn't engage with, they're taking it as a negative, but that also is not very good because maybe the customer's intent was not that kind of product. But now because, for example, you are showing laptop and phone, if the customer doesn't click on phone, it doesn't mean phone is bad, it just means that the customer had an intent for the laptop. So, or sometimes it can be that the phone is bad too, if the customer has intent for phone. So it's just this signal that something is chosen, or this signal that this observation that something is not chosen can have different interpretation. But they are saying, fuck it, we will take any clicked as a positive and any unclicked as negative. We sample all the skipped items that were ranked above the engaged item in the logged SVRP. So if you are an item above the item that is chosen, you are definitely negative. This is their assumptions. The representation of each record is now dependent on the individual item's representation. And the representation of the items ranked above it, okay, no, I read it bad. Okay, the representation of each record is now dependent on the individual item's representation and the representation of their items ranked above. Perfect. All right. So D of Q less than D is all of the items above D once we retrieve items for the query Q, I guess. Up to a property defined attention window. Properly defined attention. If we consider G theta 2, which was context aware DCG, to be a GBDT, generative body building GBDT, what is GBDT? GBD gradient boosting decision trees. All right. We can use lambda mart, again lambda mart, and if J theta 2 is linear, we can use DCG weighted cross entropy and train a logistic regression function that they like. Now we are in DPP, which is detrimental point process, which we already talked about it previously. Oh, I have to wait for an email, by the way. For my camera. Maybe it is in the scam. Spam. Social updates. Nothing. CPR. I am waiting from CPR. I will give them a call later. All right. Detrimental point process model. We explicitly define a probability distribution on sets based on is it? So it's not detriment. It's determinantal. All right. Determinantal point process tries to maximize the volume, right? Determinantal point process model, we explicitly define a probability distribution on sets based on determinant of a suitably defined kernel matrix, which probability of Q of Y, what is Y, depends on determinant of L of Y, which in turn defines a trade-off between the quality and diversity to discriminate between desirable and undesirable sets. For discussion on modeling and parameterization of this model, please refer to this. For training the model, we need to collect desirable and undesirable sets as training data and train the DPP on a binary cross entropy loss to make the problem computationally tractable. We bound the size of the record sets of items to be constant k. A desirable set is a k-subset of subsequent items in a logged SRP such that explore different constraints on the position of for negative. What is negative? K-subsets, we will take subsets of subsequent. What is that? For negative k-subsets, the ones that are not clicked, we will take subsets of subsequent items in a logged SRP such that there is no engaged item within or ranked above the subset. There is no engaged item. All of the what? Okay, fuck that, I didn't get it. Implementation. Okay, yeah, here we have some new. Actually, no, all of them are old now. We learned them. Yeah, we are getting too much formulas on mathematics now. But it's good, we want to learn it.
Implementation. In order to consolidate the new design, we elaborate in this section on the essential mechanisms identified above, and their corresponding technical components, for the proposed algorithms, MLRLTR, and DPP, and compare them with a simple baseline mechanism based on naively matching the impression distribution and the demand distribution. 1. Producing
So if we wanna consider the set of intents, the way I was designing the mechanism design truthfulness, let's say intents are vectors. Alright. What are the categories? I don't know, how can two products from different categories be in the same vector space? So all of the products are in the same vector space, which is blind to the category. And their angles. Well, the thing with that is that the dimension of that space kind of limits the category, number of categories.
Score for items. Base. We rely on standard ranking scores produced by the second round ranker as the quality scores. MLRLTR, DPP, we will still rely on standard ranking scores, suitably normalized. 2a. Defining cross-item similarity in the search context. Base. Item similarities in a given query context are computed based on a simple, one-hot.
Oh, it is one-hot actually.
Of the items based on a set of global aspects. Each coordinate of the representation vector is an indicator variable. 1 equals comma.
So each item is item similarities in a given query context are computed based on a simple 100%, based on a set of global aspects. We have global aspects, which is each dimension of that vector. Each coordinate of the representation is an indicator variable. A can be a matrix, or what is it? Is the aspects, defines which aspect, and equals V. What is V? Is the vector, where A is the aspect name and V is the aspect value. What the fuck? A is aspect name, V is aspect value, A of D will be V. Okay. For example, a new 1000 fixed price 10 item. D for a new game. What is this? We have a vector representation as follows. V of D, 1 of A, D, A in A, V in VA. This is really difficult. So what is it? I think new is an aspect of the product. If the aspect is new, it is like 1000. Fixed price is another aspect of a product. Is it fixed price or is it auction? 10. So VD will be 1 AD equals V for each A. Given this representation, we can wait trivial and operation each coordinate. That is okay. That sounds good. Both of them have in common. Similarity is the dimensions they both have in common. So it is kind of similar to our Q representation in extended representation and intentions we have. This is a good, actually, good similar. This is something natural that comes to your head. So we have these different aspects. Each aspect is a dimension, and we have these vectors, or I don't know, 10,000 dimension, and their similarity is the number of the dimensions they have in common. This also, this representation is global. It doesn't relate to the query at all. It is just global. Oh, dude, we had to read this paper before. This is not a paper, but we had to read this before starting our own. Well, now I think I can find a friendship between the two models, however. There we use 0, 1, and even if two have the same 0, it means they are similar. So here the model is 1 hot. And I think we can have a mapping that codes the 1 hot to the coding we had. So that's not a big deal. That's not a big deal. Yeah, we start from left. The number of your similarity with, for our truthfulness mechanism, truthfulness mechanism, well, I think that not having order is nicer because why? Because yeah, it's very easy. For any item we have on the website, we have a global vector, global vector. But here I'm assuming that they are sorted kind of from the most important feature in the leftmost position and towards the right, minor details. So it is, for that, similarity is number of shared bits from left, starting. We can change that. So if you wanna go one hot and we have these 2 to the n, for example, space, not 2 to the 0 and 1 to the n, which n is the number of categories aspects, which I show by k, right? So 0 to the power of k. So what are the search queries? That's nice. That's actually okay. Now we know what we are working with. Now, how can we categorize a product? Each category is kind of a similarity metric between the two vectors d and d prime. Okay. Right. Which also is very similar. We take the first three elements of the vector. We can assume each q is a vector, is a matrix A, which times A times AT, if it is equal to 1, for example, then it should be in the search result. Now, for example, A is all the ones that all of the major vectors that their first coordinate or element is 1. This is a category. So each category is a subspace. Well, that will be 2 because we have infinite number. That can be 2 actually. Let's go further. We can say like different. How far is this vector from the subspace? But still, I feel the one hot encoding and the model B hat are very close. They're very close. What I like about this one, the one hot, is that regardless of the query, we are assigning a vector to each product. Aspect name and these aspect value. We note that this representation is global and does not incorporate search history. I love this. Represent for items is computing the similarities between 2 items is a linear combination of the coordinate-wise similarities. So similarity between D and D prime is summation over any A and any V. Coordinate-wise similarities. AVQ, A and V of D and D prime. So over all matrices and over all values, we are similarity-wising it. And what is theta? Note that the linear coefficients theta 1 can potentially come from a machine learned model. However, the linear coefficients of the model in production are not machine learned and instead linear coefficient. Represent the GMB. What is GMB again? Gradient method booster. Generalized method of moment. Where's GMB? Share of aspect value V among the potential values for aspect. Historic states for query Q, for example, suppose that the only relevant aspect is same type and the historic demand GMB is distributed like 80%, 20% auction. 80% fixed price, 20% auction. Theta of auction 0.2, theta of fixed price is 0.8. And ML, RLTR, DTP, we train a similarity function. I need to read it again. I'm missing something here. Well, while reading now, so we had the 1 hot, we had the theta 1. Now, okay, similarity based on aspect's name and aspect value of two items D and D prime is if their aspect name and value match, right? Then the similarity, general similarity between D and D prime is sum over all these similarities over aspect and values that match based on this combination coefficient that is thetas, linear. Suppose the only relevant aspect is sale type and historic demand GMB. What is GMB historic demand? GMB historic demand. Google My Business. Is it it? Oh, okay, Google My Businesses.
GMB historic demand typically refers to analyzing or understanding the past demand for a product, service, or resource within a specific context or market. While GMB could refer to various things depending on the context, one common interpretation in business and marketing contexts is Google My Business, GMB. However, if you're referring to a different domain, please clarify. Google My Business, GMB.
So these thetas, actually these thetas are exactly the same theta we had. But at the beginning of it, it said we don't use this kind of, it said we use granular something. MLT, RLT, we train a similarity function, theta parameterized by theta 1 based on a combination of different modalities. Note that the crucial difference between PROD is that we will be able to train theta 1 with the, so training theta 1 means finding theta 1 and those theta AVQs with the approaches explainable to learn theta 1, theta 2 jointly. While we cannot, you go ahead, I'm tired.
While we can use the same global aspect representations as ROD for our initial iteration, we are experimenting with including richer modalities of the items, including titles, images, and non-global aspects, incorporating suitably trained item embeddings. Note that we can use embeddings trained for a generic conflict prediction task, or we can have fine-tuned embeddings for a suitable task and learn similarity scores that are query context specific.
No, so we can also set similarity metrics based on. Fuck off.
More effective way.
So these are not just the descriptions, these similarity features. They can be the photos you post, and they can be the, what else? Image, title, image, non-global aspects. Code-click prediction task, or we can have fine-tuned embedding for a suitable similarity scores, similarity theta 1 that are query context specific. We add a query argument inside this. While multimodal embeddings are a more effective way of incorporating multiple modalities in the item representations we use for similarity computing, we can still rely on separate representation per modality and learn a suitably parameterized model that combines multiple modalities. M in M. M is modality. Computing the similarity score is G of similarity on modality M, sum over modality and Q. Alright, these are nice. Now, how can I relate it to other things we talked about? We had a truthful mechanism, and we also had another thing that items are exactly similar. There is only one category left, but it's not obvious based on the product's description, but based on consumers' behavior. If it is not based on product description, I don't know what to do with it. Guys, I say 1 round and a half, and then we will come back here. Okay, fuck 1 round and a half, but I need some time. Just digest it so far, and then we will go the rest of it, because it wants to go further and comes with 2 other methods and has algorithm, and then we get to appendix, which is really good, by the way. All of the math is here. So yeah, let's not play counter because it just distracts us. Oh, fuck, dude. Query is Q. D is the item. Capital D is set of all the items retrieved for Q, DQ. V of D. Each item has a vector representation. which is called V of t. The size of V of t is quality of the product. Size of V of t is quality of the product. The angle they make with each other represents for their similarities. However, this similarity metric that they talked about here is a bit different. And then utility of this utility from a ranking or from a list is the space the items in that list make with each other. That's one. Then we said what did you say? So that was that. But now we came to the determinantal point processes, right? So what else we had? We had the ranking pi. We had the probability of sale given the ranking and this, and then we are okay. They were context oblivious. Now we went to context aware ranking that says, okay, if two items are similar with each other, they kind of steal each other's click through rate, right? So now we need to compare each item with all of the items above it, and we need a more complicated version of what is this called, the ranking, DCG. All right, and then we say that for query Q, what is score of each item? What is the score of each item for query Q? Then we compare it with all of the items above that item in the list, and we consider the measure of similarity between them, and also for query Q their score. And then we say kernel of the matrix. Now defining cross-item similarity in the search context. Defining cross-item, two items, D and D prime, what is their similarity? The thing is that we have a global representation of each item. Here I have the problem that the size of the vectors is not their quality, just features of the product and description. And it is one hot, so if you have this feature or if you are in this category, that dimension will be 1 for you. Then the symmetry between two products is the number of okay, it's more complicated than the number of dimensions you have in common, but it is for any aspect name like A, matrix A, and any aspect value V, how many of them you have similarity, you are the same. This aspect value, the getter function. So a new fixed priced item, D, we have a vector representation as, I get 1 0 0 1 0, but I don't get the 0 1 at the end. Given this representation, we compute the similarity between two items by trivial AND operation. Okay, I didn't get this part. Now similarities between the three is between over summation over these thetas, and we want to learn these thetas. And then he says we can have similarity based on query Q and modality. Okay. now we want to talk about computing similarity to slotted context given pairwise similarities. Given pairwise similarities. What is he saying? Computing similarity to slotted context given pairwise similarities. Alright, so we have pairwise, each two item, I see, okay. Pairwise similarities, what does that mean? Each two items, we have the similarity between them. Now, can we find the similarity in the whole list given that we have the similarity between each two? Sounds like that.
Of incorporating multiple computing similarity to slotted context given pairwise similarities. Base. Given a set of pairwise similarities between a candidate item and an item context, set of already placed items are computed based on applying a simple attention/aggregate function to the pairwise similarities. Comma.
So similarity of item D with all the products above it is aggregate of similarity of D and D prime where D prime belongs to. Okay. Note that the aggregation function can be as sophisticated as it gets by using a proper attention mechanism with adjustable window size. This attention stuff are machine learning, which is really good. I like this approach. But we are currently using a vanilla mean pooling scheme. So it is the mean of the similarities of all the items above it. We will be exploring a simple attention mechanism to adjust the effect of proximity position of the previously ranked items with respect to the hand. Similarity theta 1D and all the items above it equals the sum over all the items above it, lambda to the pi D prime similarity of the item. So it is a weighted sum. The attention parameter lambda can be learned as part of the parameterization parameter theta 1 in an empirical study by Airbnb. They show that lambda 1/3 lead to the best NDCG. DCG is discounted cumulated gain. NDCG is non-discounted or natural in their search diversification method. DPPP, determinantal point process. The similarity aggregation cross item is embedded in determinant computation, and the similarity with respect to the set is not a vanilla aggregation of pairwise similarities, and it depends on interaction. The DPP sequential ranking scheme, there is no way to adjust attention on previously placed items. Okay, sequential scoring ranking model. Section 3. Okay, that one was not very difficult and complicated. 3A is sequential scoring ranking model. Okay, give some time, free some space in my brain. Oh shoot. Okay guys, I have to. Yeah. Okay. The moment you take a break, other thoughts come to your head. Bruh. Okay, let's go the rest of it. Alright. I will finish 3A, 3B, and appendix for another time. Alright. Sequential scoring ranking, re-ranking model. RLTR is relational ranking to rank, learning to rank. All right.
Sequential scoring re-ranking model. Base. We use the relational learning to rank, RLTR, framework with a linear re-ranker to combine the quality scores and the similarity scores. This logic can be implemented.
We use the relational learning to rank framework with a linear re-ranker to combine the quality scores and the similarity score. Well, quality scores leads to flooding. Similarity scores leads to too much diversity. Mix of it is good, right? This logic can be
as a convex combination of the normalized quality scores and a linear combination of 2 plus.
So it is RQD should be quality score. RQD, 1/2 RQD, 1 minus 1/2 similarity of D of and other items above. What is RQD? Is the quality. This technique can be understood as an ad hoc push-pull mechanism to control the share of items from different aspect value pairs to coverage at each placement more towards the distribution weights of the models. We note neither the coefficients for computing this nor the trade-off parameter lambda is not machine learned. Lambda RQD 1 minus lambda W AVQ similarity of AV of the NDQ above. If we rely on a linear re-ranking logic for GDQ was the context-aware DCG. G theta 2 RQD is here. It used to be F of QD. Alright, we can use the existing RLTR blender to re-rank the items. Algorithm input. Oh, fuck, dude. Actually, this is still a question. How do they choose the set DQ? That's about logging and retrieving information. The phone is there. So we choose set DQ input. Place item PQ, top sponsored item or items from previous block. Pairwise similarity, Sij, through a custom similarity function. Quality, so we have any two pair items similarity matrix. We have all the items that are above item D, like up to location N, and we want to choose the product or item for location N. Quality score Ri. So now for query Q, we have a context oblivious metric that says just sorts them, disregards based, regardless of their similarity, sort them. And aggregation function often mean to aggregate pairwise similarities. Initialize result within ranking block RQ is empty as long as the size of RQ is less than K. DJ is argmax of DI minus RQ minus PQ. It's not at the top. Minus RQ. What is RQ? So far chosen. Log of RI. What is RI? Plus log of aggregate of similarity. So argmax of it. Then we choose the DJ. So DJ actually, why should we be argmax? Ri is the score of that product, right? It should be minus log of the aggregate similarity, right? It should be the minus log because similarity is not good. We said we want a linear combination, right? Do you remember? We said we want a linear combination of score, the, what was it called? quality score and similarity score. We don't want similarity score to be very high, so the plus should be actually minus. Yeah. Oh, it is 1/2 similarity. Well, why similarity comes at the top? Yeah, actually, lambda and 1 minus lambda helps better. Lambda says the amount of weight we want to put. The more weight you want to put on the quality, the less weight you want to put on similarity. We don't want to put weight on similarity, we want to put weight on anti-similarity. Like, what is the definition? Opposite variety or something like that. Diversity. This is saying put products that are similar at the top. I don't like that. Okay. The DI that is getting argmaxed, here is the important. That DI does not belong to the products already in the list. Right? So that product already. Well, of course it should not be, but actually I don't get this part. Why it should be some? Yeah. Is it? Determinant of RIJs. Alright. There is a trade-off between quality and diversity, but I think the objective function here does not show it. So we need a new blender to sequentially update the place item with the following. The complexity of algorithm will limit the iteration window to small value k. Sequential KDPP with no intra-block attention. Honestly, instead of sequential, say tree, horse, simple words. Input. Candidate DQ, placed item PQ, sponsored item previous block, pairwise similarity, USIJ, through a custom similarity function, quality score RI, and initial result is set with arv is 0 empty, HI ranks the highest, dynamic context score CI is for each DI. If RQ less than K, DJ argmax of HI, which was the score. RQ is at DJ for all the DI that are not in DQ but are not ranked yet. TI, compute the TI, which is all TI. Your TI is in reverse relation with HI, your ranking regardless of others. Then you have your SIJ, and your ranking kind of minus the dynamic context score, CI, and then you extend CI, and this is happening here. And for what? Computing SIJ should be counted as the most expensive. So similarity between two items is the most difficult part. Other parts are easy. Scores T. Oh, okay. this is a really good framework. This was a very good framework for me. Still, some parts of it are vague, ambiguous, and similar to the set of already.
Controlled computational complexity. Base. There are three components in characterizing the computational complexity of a set ranking algorithm. 1. The candidate set size for reranking, and 2. Attention window size, or the effective number of selected items that the similarity of the candidate item has to be compared against. 3. The cost
By the way,
of
there is no
similarity
dandruff
computation.
here.
The RLTR blender considers a maximum of k items as candidate items for reranking and reranks the top kk items on the page 11. The similarity of the candidate item is calculated against every item in the set of already selected items. Since similarity features are binary, computing cross-item similarity for a pair of items needs adding element-wise binary ANDs per dimension. Thus the computational complexity is O, NKD, where k is the number of placed items, nk is the number of remaining candidates, and d is the number of similarity dimensions.
Okay, I didn't listen to that.
MLRLTR. There are three components in characterizing the computational complexity of a set ranking algorithm. 1. The candidate set size for reranking, and 2. Attention window size, or the effective number of selected
Which
items
is
that
K.
the similarity of the candidate item has to be compared against. 3. The cost of similarity computation. The RLTR blender considers a maximum of k items as candidate items for reranking and reranks the top kk items on the page 11. The similarity of the candidate item is calculated against every item in the set of already selected items. Since similarity features are binary, computing cross-item similarity for a pair of items needs adding element-wise binary ANDs per dimension. Thus the computational complexity is O, NKD,
That's
where
a
k
big
is the
number.
number of placed items, nk is the number of remaining candidates, and d is the number of similarity dimensions. MLRLTR. We can maintain the same complexity as base if we use a linear reranking logic. The only increased complexity can come from using richer representations for similarity computation, increasing DPP. The main complexity is in computing the temporary scores for all the candidate items set membership symbol / at each placement, which leads to O, NKD, complexity. We control the complexity by limiting effective block size K appendix.
Alright.
Statistical framework for
Fuck
setting.
this. Okay, we have to read the appendix, really helps us. But we learned a lot. Okay, 1 round and a half. I finished the video. I will call, see what happened to my camera, and then if they say it's ready, I will go take it. If it's not, we will shoot another video with the iPhone. But it was great idea not to play counter in the middle of the study, ever. Okay. And actually, I like the way they model the problem. These vectors, we have the D, which is global. Doesn't feel comfortable, to be honest. Oh, everybody has a snack, so. Oh. I'm the sniper. Oof, that was a close. Shit. Optimus Prime killed me. Again, Optimus Prime. Bitch. Shit, they are now ready here to kill us. Let's go! That was so bad. Why are we all down here? First time it happens in the history of Counter-Strike. They are better than us. Finally. Oh, don't kill us, brother. Bitch, go ahead. That was a good round. Had fun. Three. Dude, I don't have comfort doing this. Go, 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 go. Okay, we are over. So many people there. I just don't like this way of. Where are you? Why are we here and nobody's there? There's nobody. Where are these? Suddenly, three of them showed up. Fuck, okay. Interesting, everybody wants to go to the shoots, not the pool. Yeah, don't play counter in the middle. That should be my role model. Yeah, either finish your session by a counter or the thing is that you need some time to like the stuff I read just gets to the point that are too much, and then I say, okay, I cannot continue. Then I need some break. But counter is just putting myself in another complete different world. In a way that I say, oh, what happened? Where have I been? You know, I just need some more time. Bro. Okay. Oh, the double mice also is here. Come over, bitches. Don't jump, motherfucker. I knew. Punana killed me. Hahaha, Punana killed you. Ah, real noob. That's the double mice. I got my buddies back. Ah, fuck! I knew! Alright, don't go forward because they're all here. Oh, even then they killed me. Come over, bitch. Woo, I killed you. I killed you too, motherfucker. Now I have a real... Where are these motherfuckers? I'm not going ahead. I'm not going forward. They come here. Oof, 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 oof. Oof, didn't I tell you? Oh. What am I doing? Dude, fuck. What's going on? Bro, I'm just hitting his head. This motherfucker Hollow still has... How did that happen? Oh fuck, why do you change the gun, motherfucker? Ah! I hate this keyboard. Where? Oh, okay. Honestly, Hollow killed 4 people and they're all me. 5 people and they're all me. Ugh. I don't care if you're vexed or not. Hey Vexed, how are you doing? Dude, he killed better. It's all about being calm at the end of the day. one also being... Oh, shit. Doesn't matter if you're vexed or not. Oof. Ah, it was right click. Alright. I see, bitch. I'm one of the top dogs here, bro. Hollow killed me so bad. Oh. Banana, motherfucker. I wanna kill you, motherfucker. I wanna kill you, kill you. Ding, 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 ding. Bitches. What about that, huh? Yeah, motherfucker, yeah. Ooh, 3 people have knives. This is the gang of the city. Ooh. Optimus Prime is nobody. Oof. Actually, I was the second person in my group, but real noob. Puna and wait. First one, 31B. Because this is an amazing group, I will go one more round. Oh, bitch. Oof, bitch. Okay. I really think, well, real noob is here for sure. Yeah, Vexed is here for sure. Gangs are here. Bro, don't bring me here. This is the worst position. I told you. Fuck, dude. I hope she's understanding. Ah, fuck! Oof. I can see his face crushing up. This is a new gamer. Okay. There are good gamers here in this. Fuck you! Who wants to drink water here? Oof. Oh, dude, this is a good. Fuck, dude. He got too much machine gun. Oh, bro. This gun. I have no chance with this gun. I have to get my knife. Fuck this. They're... Okay. Oh my god. These motherfuckers know how to kill us. I think I'm the worst. Ooh, I killed somebody. Okay, finally got rid of my snipe. Wow, they made it. Punaner. He makes it in the knife suddenly. Alright, why am I going ahead? They're better. It's just stupid. Wait for them. The guy comes with his knife. I'm scared. I'm just scared. These real motherfuckers. They're real motherfuckers. Dude, we need to do another pool actually. This is a mayhem. The guy is just jumping with a knife and killing everybody. Fuck. Wow. Real noob was on our side. Punaner won. Woo! Even like real noob, nothing close to Punaner. Anyways, let's go. I'm not gonna play another. Damn, in shoots I was doing good. And suddenly, this, oh, I didn't check how he did. Anyways, this guy was killing all of us at the beginning and it took me so long to get the snipe.